Imagine a world full of giant reptiles and lush tropical forests, a world that had thrived for over 180 million years. Then, in what seems like a geologic blink, three-quarters of Earth's species, including all non-avian dinosaurs, vanish. For more than a century, scientists puzzled over this mass extinction. Ideas ranged from disease and climate change to volcanic eruptions and even a nearby supernova. In this story, I want to take you along on the scientific odyssey that eventually pinned the blame on a cosmic catastrophe. The impact of a 10 to 15 kilometer wide asteroid that slammed into what is now Mexico and radically changed life on Earth. The tale involves a father and son, an unusual metal called iridium, a search for a crater hidden under kilometers of rock and water, and decades of controversy before a consensus was reached. By the mid-1900s, paleontologists knew that dinosaurs disappeared at the boundary between the Cretaceous and what used to be called the Tertiary period. This boundary marks the end of the Mesozoic era and the beginning of the Cenozoic era. Fossils showed that above a thin clay layer, dinosaurs were gone while mammals and other species diversified. But what caused this sudden break? Earlier explanations often mirrored the limited understanding of Earth's systems. Some scientists suggested gradual climate change or competition from mammals. Others, noting that earlier mass extinctions correlated with huge volcanic eruptions, proposed that the dinosaur extinction might have been caused by volcanic activity, such as the massive lava flows known as the Deccan Traps in India. There were even wilder theories, including a nearby star exploding in a supernova and bathing Earth in lethal radiation. Each idea had its proponents, and none could account for all the evidence. Our story really begins in 1977 in the hills near Gubbio, Italy. Geologist Walter Alvarez was studying the magnetic reversals recorded in ancient limestone in order to date rock layers. At one road cut, he noticed a thin band of clay separating the fossil-rich limestone of the Cretaceous from the relatively barren limestone of the Paleogene. Below the clay, tiny shelled organisms called foraminifera flourished. Above it, only a single species remained. The clay layer clearly marked a moment of cataclysmic change. But how long did it represent? Did this transition happen instantaneously or over hundreds of thousands of years? Walter shared his curiosity with his father, Luis Alvarez, a Nobel Prize-winning physicist known for his work on particle physics and radar. Luis suggested measuring the concentration of iridium, an element that is extremely rare in Earth's crust but relatively abundant in meteorites. If they could measure iridium levels in the clay, perhaps they could estimate how long it took to accumulate. A long deposition would contain only background levels of extraterrestrial dust, whereas a high concentration would suggest a sudden influx from a cosmic source. To make this measurement, they enlisted two nuclear chemists at Lawrence Berkeley Laboratory, Frank Asaro and Helen Michael, who specialized in neutron activation analysis. When Asaro and Michel analyzed samples from the clay layer and compared them with samples from the younger and older limestone, they found something astonishing. The clay was about 25 times richer in iridium than expected. Later analyses showed enhancements by factors as high as 600. Because iridium is scarce in Earth's crust, but common in meteorites, the team suspected that the clay's iridium spike came from extraterrestrial material. Crucially, similar iridium anomalies were soon found at KPG boundary sections in Denmark, New Zealand, and other sites. The discovery of high iridium concentrations at multiple KPG boundary sites convinced scientists that the impact must have been huge. As scientists tried to rule out alternative sources, they found the iridium pattern inconsistent with a supernova. By looking for isotopes such as plutonium-244 that would have been produced in a nearby supernova, Asaro and Michel found no signal, effectively ruling out the supernova hypothesis. With other explanations failing, the Alvarezes formulated a bold idea. A large asteroid or comet impact had struck Earth 66 million years ago, blasting iridium-rich dust into the atmosphere and depositing it worldwide. The father and son team, together with Asaro and Michel, published their hypothesis in the journal Science in 1980. They argued that an impactor several kilometers in diameter would have released energy far exceeding the combined force of all human nuclear weapons, hurling molten rock and dust into the sky. This debris cloud would darken the skies, causing a nuclear winter, collapsing photosynthesis and the food chain, and causing global wildfires and acid rain. Their calculations suggested that such a catastrophe could wipe out most life on Earth. The paper was revolutionary and controversial, igniting debate across disciplines. Many geologists were skeptical. Some dismissed the idea as sensational. After all, there was no known crater of the predicted size. Others preferred volcanic explanations, such as the Deccan traps. As Asaro remarked, they needed a satisfactory theory of the extinction that matched all the data. Yet evidence supporting the impact hypothesis mounted quickly. At sites around the world, researchers found shocked quartz grains and tiny glassy droplets called microtectites in the same clay layer as the iridium anomaly. Such features form only under the extreme pressures and temperatures of an impact. In Haiti, geologists Alan Hildebrand and David Kring discovered an unusually thick layer, up to 46 centimeters, of impact melt spherules and shocked quartz at the KPG boundary. The thickness of this deposit suggested that the impact site lay somewhere in the Gulf of Mexico or Caribbean region. The search for the crater intensified. At the same time, oil industry geophysicists Antonio Camargo and Glenn Penfield were mapping gravity anomalies for Pemex, the Mexican state petroleum company. In the late 1970s, they identified a semicircular structure buried beneath the northern Yucatán Peninsula. The feature had been drilled for oil and interpreted as a volcanic complex. However, Penfield suspected it might be something more. When he later read about the impact theory, he realized that this buried structure might be the missing crater. In 1990, Penfield and geologist Alan Hildebrand connected these observations. When core samples from the Yucatán boreholes were re-examined, they contained shocked quartz and impact melt rocks, definitive evidence of an asteroid strike. In 1991, Hildebrand and colleagues formally announced the Chicxulub crater, a roughly 180-kilometer-wide impact structure centered near the town of Chicxulub on Mexico's Yucatán Peninsula. Gravity and magnetic data showed a huge bowl-shaped anomaly buried under a kilometer of sediment. Dating of the crater's rocks indicated an age of about 66 million years, precisely coinciding with the KPG boundary. The crater's size and age matched the predictions made by the Alvarez team. The discovery of the Chicxulub crater did not instantly end the debate. Throughout the 1980s and 1990s, some researchers pointed to the enormous volcanic eruptions of the Deccan traps in India as a cause of gradual environmental stress. In fact, a 2010 article in Science reported that dozens of scientists still challenged the impact explanation and argued for volcanic or multiple cause models. Nevertheless, the weight of evidence increasingly favored the impact theory. Geochemical analysis showed that Chicxulub impact rocks contained shocked quartz, melted granite from deep within Earth's crust, and no gypsum, indicating that the impact had vaporized sulfate-rich rocks and injected sulfur aerosols into the atmosphere. These details explained how the impact could have dramatically cooled the planet and poisoned the oceans. Further corroboration came from drilling and dating projects. In 2016, an international team drilled into the crater's peak ring and found granite that had been shocked, melted, and ejected to the surface within minutes of the impact. They discovered almost no gypsum, implying that sulfur-bearing rocks were vaporized and injected into the atmosphere, supporting models of climate disruption. Additionally, argon-argon dating refined the age of the impact to 66.038 plus or minus 0.011 million years, and high-resolution studies of fossil bones suggested that the asteroid struck during Northern Hemisphere spring. In March 2010, a panel of 41 experts reviewed 2 decades of research and concluded that the Chicxulub impact was the ultimate cause of the mass extinction. They dismissed alternate theories and noted that the impact likely occurred in a sulfate-rich area, amplifying its climatic effects. This effectively ended the scientific controversy, though work continues to understand the environmental cascade triggered by the impact. Modern estimates suggest that the asteroid impact released energy equivalent to 100 million megatons of TNT, surpassing the world's nuclear arsenal. The explosion excavated a hole 20 kilometers deep and 150 to 200 kilometers wide, ejecting molten rock and dust into the atmosphere. The impact caused massive tidal waves, global fires, and long-lasting atmospheric darkness. Photosynthesis collapsed, food chains broke down, and, within a geologic instant, most large animals perished. The death of the dinosaurs cleared ecological space for mammals, including our ancestors, to radiate. Yet the story is more than a tale of devastation. It is a parable of scientific persistence and collaboration. Walter Alvarez's curiosity about a thin clay layer led him to enlist his father and colleagues from a different discipline. Frank Asaro and Helen Michaels' expertise in nuclear chemistry provided the critical iridium measurements. Geophysicists exploring for oil unwittingly mapped a crater that would become central to paleontology. Geologists and paleontologists, analyzing fossils and rock layers across continents, supplied context and additional evidence. Each field contributed pieces of a puzzle that, when assembled, revealed a single, catastrophic event at the dawn of the Cenozoic. Perhaps the most sobering lesson of the Chicxulub story is that Earth's biosphere is vulnerable to sudden, external shocks. Catastrophic impacts are rare but real. They have reshaped the evolutionary trajectory of life. Recognizing this vulnerability has led to the creation of programs to track near-Earth objects and plan for potential deflection missions. It has also inspired deeper research into how ecosystems respond to rapid environmental changes. Justice Fermat's last theorem was solved through centuries of incremental progress and a final leap of insight. The mystery of the dinosaurs' demise was unraveled through decades of multidisciplinary work, culminating in a breakthrough. For more than a century, scientists argued about gradual versus catastrophic causes. In 1980, the Alvarez's bold hypothesis reframed the debate: the discovery of a global iridium anomaly, the presence of shocked quartz and microtectites, and the eventual identification of the Chicxulub crater built a chain of evidence that became impossible to ignore. Today, the impact theory is not merely a hypothesis, but a cornerstone of geologic and evolutionary science. It explains why the age of dinosaurs ended and why mammals rose to dominance. It reminds us that chance events, an asteroid colliding with a planet, can alter the course of life. And it highlights the power of curiosity, collaboration, and persistence. A thin layer of clay sparked one of the most exciting scientific detective stories of the 20th century, ultimately revealing that our world can be changed in an instant by rocks from space.